Hello, I'm Dina, a final year cybersecurity student at Teesside University. And today I'll be presenting my project on indoor emergency personnel tracking. To begin with, this project focuses on tracking emergency responders in indoor environments where traditional systems such as GPS are ineffective. In critical situations like fires or building collapses, it becomes extremely difficult to determine the exact location of responders inside the structure. To address this issue, I designed a wireless sensor network based tracking system using 32 sensor nodes arranged in a structured corridor layout. The system was simulated using CupCarbon to evaluate its performance before any real-world deployment. As a result, the system achieved highly promising outcomes, included a 100% packet delivery ratio with zero packet loss, which demonstrates very reliable communication. Firstly, emergency responders often operate in highly dangerous indoor environments where visibility is low and conditions are unpredictable. Without proper tracking systems, coordinating teams and ensuring responder safety becomes extremely challenging. For example, in a firefighting situation, if a firefighter becomes lost or trapped inside a building, locating them quickly can be very difficult. So traditional tracking systems like GPS are not effective in these cases. They are not effective indoors due to signal attenuation and interference caused by walls or structures. Therefore, wireless sensor networks are considered a strong alternative as they enable communication without relying on external infrastructure such as satellites or Wi-Fi. In terms of the problem, the main issue addressed in this project is the lack of reliable tracking solutions for indoor GPS denied environments. Existing systems often rely on expensive infrastructure, such as Wi Fi access points, which may not be available in emergency situations. In addition, indoor environments introduce challenges such as signal degradation or obstruction and unpredictable movement of personnel. As a result, there is a clear need for a solution that is flexible, cost effective, and reliable in real time emergency conditions. Now, to provide some background, wireless sensor networks usually consist of small, low power sensor nodes that communicate wirelessly. These nodes collaborate to transmit data using a multi-hop communication approach, which information is forwarded from one node to another until it reaches its destination. Moreover, WSN are usually commonly used in monitoring and environmental sensing applications. Importantly, they are especially suitable for emergency scenarios because they do not depend on centralized infrastructure and can function in isolated environments. From the literature review, from the 5 papers I researched, several limitations in existing research were identified. Firstly, many systems still rely heavily on GPS or Wi Fi, which are unreliable in indoor environments. Secondly, most research focus on hardware implementation rather than a simulation based validation. Furthermore, node placement strategies are often unstructured, which leads to inefficient communication. Finally, packet level performance metrics such as delivery ratio and loss rate are not always properly evaluated. Overall, these gaps highlight the need for a structured simulation driven approach to indoor tracking systems. Moving on to the proposed systems, my system consists of three main components. Node sensor 1, which acts as the transmitter responsible for sending tracking messages. Node sensor 2 to sensor 31 function as relay nodes, forwarding data across the network. Finally, node sensor 32 acts as the receiver where all tracking data is collected and logged. So, sensor 1 is here. From here, sensor 2 until sensor 31. And here is sensor 32. Okay. In this way, the system uses a structured multi-hop topology where data travels step by step through a predefined nodes without relying on external infrastructure. This slide illustrates the system deployment and data flow. A total of 32 sensor nodes are arranged across four connected corridors in a structured layout. Now, to explain this in a practical scenario, imagine a firefighter moves through these corridors inside a building. As a firefighter moves, their tracking data is transmitted from the source node over here and passed through multiple relay nodes. Each node forwards the message to the next one until it reaches the final destination over here. As a result, this structured multi-hop communication ensures stable, predictable, and reliable data transmission even under dynamic movement conditions. To further clarify, let's consider a real-life emergency scenario. Imagine a firefighter enters a burning building, during a rescue operation. The firefighter is equipped with a device connected to node sensor 1, okay, which continuously transmits status or location information. As the firefighter moves forward, as they move through different corridors, the signal is not sent directly to a central system. Instead, it's passed from node to node, from sensor 2 to sensor through to sensor 31, forming a communication chain. Each node acts as a relay, ensuring the message is forwarded correctly and without interruption. Finally, the data reaches node sensor 32, which acts as the receiver and logs the information for the control team outside the building. Therefore, this ensures real-time monitoring without relying on GPS or Wi-Fi. In terms of performance, the system was evaluated using a total of 32 sensor nodes. The simulation ran for 1874 seconds, during which tracking messages were continuously transmitted. Performance was measured using key metrics such as packet delivery ratio, packet loss, and system stability. The results were very strong. A total of 1,874 packets were sent, and all 1,874 were successfully received. There was zero packet loss throughout the simulation. Thus, the system achieved a 100% packet delivery ratio. These results clearly demonstrate that the structured topology provides highly stable and reliable communication even under continuous data transmission. To conclude, this project presented a wireless sensor network-based solution for indoor emergency personnel tracking. The system successfully demonstrated reliable communication in a simulated environment with excellent performance results. Importantly, the structured multi-hop design played a key role in providing or in improving both efficiency and stability. Looking ahead, in the future work, the system can be extended into real hardware implementation, enhanced with advanced localization techniques, expanded to multi-floor environments, and integrated with real-time dashboards and security features. Those are the references I used in my research, and that was it. Thank you very, very much for listening to my presentation.